I restarted. Here we go.
I see it.
Greetings and welcome, ladies and gentlemen. Today we're talking about radical expression, so I drew this awesome little hand. It's not a dog, but no, it's my awesome, like, party on, rock on, math time. And today we're going to talk about multiplying, dividing, and adding and subtracting radicals. So good times indeed. Good times will be had by all. And let's actually talk about like a product property for radicals. All right, product property of radicals. So let's say I've got like the square root of a times the square root of b. What do you think I could rewrite that as? The square root of ab, or a times b, right? If I multiply both of those, I can, in fact, write them as one big radical and multiply their insides.
They moved in together in one house.
Wow, that's a lovely story.
Yeah.
I like it. And in fact, this is even true if I throw a little n. If these were nth roots. Nth roots. Wait a minute.
I like the end. Why is that there? It's the hobby.
Nth root. You know what I think of when I hear nth root now? I just realized. I'm thinking of Nern root. Anybody? Anybody? No? Skyrim, Oblivion. When you're walking around, it's the only plant that glows and makes like a weird humming noise when you find it. It's really good for alchemy stuff. But anyways, I guess that's unrelated. So nth root, it turns out you can actually multiply their insides. Hey, who would have known? Wow! So let's do an example starting off with something maybe we've seen before. What if I've got 2 times the square root of 6 multiplied by the square root of 10? So initially, if you look at these, square root of 6 cannot be simplified. Guys, the dump truck is here. Oh, it's taking the garbage out. This is so awesome. I wish you guys could see it. My wires are all over the place, but that's okay. Guys, you missed it. Internet friends, seriously, I hope you go watch a video about trucks. Seriously, just search it in YouTube right now. You can find it. Maybe I'll add some hyperlinks down in the comments of some really good ones. My son likes trucks. So I just want to point out the square root of 6 cannot be reduced. There's no perfect square that goes into 6. And likewise with the square root of 10. However, when their powers combine, 6 times 10 is 60. Now I can actually reduce the square root of 60. So I brought it together only to break it apart once again. Oh, it's like they moved into the same house and they broke up, but somehow they had different amounts of stuff than they started with. So what is a perfect square that goes into 60? Well, it turns out I think 4 does. And 15 times. Yeah, good job on that division. And so, yeah, it's kind of like, 6 and 10 moved in together. And then due to alimony, 6 now only has 4 because they have to pay 2 to the 10. Oh, now 10 actually has 15 now. They made out really good on the deal. So, yeah. How sad. 2 times the square root of 4. 2 times the square root of 4 is 2. And 2 times 2 is 4. Square roots of 15. So that's the general idea, is that you can multiply the insides of radicals to get bigger radicals.
2 times 2 is 15. Yeah.
Well, the square root of 4 became that 2.
Oh.
Right? Okay. Thanks for asking for clarification. Please do when you get a chance. Always ask for stuff like that. What if I've got this? Let's do this example. What if I've got the 4th root of 4t cubed multiplied by the 4th root of 8t squared v to the 5th. Bam. Ay caramba. So, first of all, 4th root of 4, can't do it. 4th root of t cubed, nope. 4th root of 8, can't simplify it. 4th root of t squared, nope. 4th root of v to the 5th, I could have simplified, but that's the only one. So what am I going to do? Eat SpaghettiOs. There's a really good commercial from back in the day of a soccer team when like the coach is giving a motivational speech, but all the soccer players are talking about SpaghettiOs. Anyone know what I'm talking about? Seriously, YouTube it right now, friends, if you're not in my class right now. Internet friends, YouTube it. Search Eat SpaghettiOs commercial. Bam. It's good. It's good. And in fact, it was my soccer team's motto when I was in soccer team. Until I broke my arm falling out of a tree. Not while playing soccer, because there's no trees in soccer fields. Guys, seriously, you thought there was a tree in a soccer... Why would I be climbing a tree in the middle of a soccer field during a soccer game? That doesn't make any sense. But ever since then, I never played soccer again. How sad. But I did go on to coach soccer. When I was in 10th grade, I coached a 12-year-old boys team soccer with my buddy. We teamed up. Cooperative coaching. What? And I lived vicariously through them and made them not ever climb trees. So, wow, that was a side story. So I multiplied the insides during that story. I don't know if you noticed that. It was amazing.
What?
And let's see. So I just multiplied 4 times 8, got 32. T cubed times t squared is t to the 5th. And v to the 5th is still hanging out. So I multiplied them as one big radical. And now I'm going to simplify that radical if possible. Is there a perfect fourth that goes into 32? No. On 2 occasions. 9 is a perfect square. And 9 also doesn't go into 32. But that's okay. I appreciate your efforts. Other attempt, 32, what's a perfect fourth?
2.
2 is not a perfect fourth.
4.
4 is a perfect square.
5, 6. 6 is 8.
Oh, we're getting warmer. That's a perfect cube.
16.
16. There we go, friends. We got it. We got it. And 16 goes into 32 how many times?
2.
Twice. And let's see, t to the 5th, I can't do that, but Jacob, there are a good number of these t's that I could simplify. Am I right?
Yeah.
So just like on the homework, yeah, I'm going to break this up into t to the 4th times the 4th root of t to the 1. One-th?
First.
One-eth? Oneth. Onth? I don't know. T to the 1st. Sure, I like that better. So yeah, just like on the little homework example, just like that. And then the same thing with the v's. V to the 4th times the 4th root of v to the 1st. Whew. Okay, let's get down to simplifying. The 4th root of 16 is 2. Actually, I'm going to make that a loop-de-2. Just I really want to right there. Forced Waldo there. 4th root of t to the 4th is t. Does Connell's rule apply? Do absolute values show up?
Yes.
Yes, because even. Bam. 4th root of v to the 4th?
Yes.
Yes. In fact, what's interesting is you actually could rewrite this, if you wanted, as the absolute value of TV.
And it's like the line on the top and the bottom, it sort of looks like a TV that's saying TV.
Yeah, it's like a little... Actually,
I
I like it. Wow. Good stuff. So, and then let's see. Now I just have everything else that couldn't simplify. Yeah, Twin Valley, represent. Right? Now this is Twin Valley Math, the YouTube page right here. So, represent indeed. 4th root of 2, 2 is still hanging out. T is still hanging out. This V is still hanging out in there too. And let's see. Does Hank's rule apply? Can I drop the absolute value around the T or the V? No, because those are odd exponents. So I think I'm just done. Box it. Thing of beauty. Beautiful, my friends. Beauty. So let's talk about division.
Never.
Let's talk about quotients. Nope. Quotient. Property of radicals. And it turns out that an nth root of a over b is equal to, let's see, I guess this is radical of a quotient or something like that if I wanted to come up with a better name for it. But that's fine. It turns out you're allowed to distribute said radical to both top and bottom.
So A is the,
Which actually, think about this. Think about it. This in the other direction, right? I technically distributed this nth root to both the a and the b. So radicals are distributive over multiplication, and radicals are distributive over division. Isn't that craziness? So, which is also true for our exponents, and you may realize radicals and exponents are really similar to each other. Foreshadowing is what that's called. Well, that was actually a little bit like really foreshadowing, like, but really blatantly with foreshadowing. It was like hit with the shadow of a club if you were Peter Pan's shadow. So let's talk about this. Actually, one other constraint, it turns out a little rule is you're not allowed to have radicals in the denominator. Never leave radicals in a denominator. And that's just like an interesting rule. It actually originated back in the days of mathematical tables, where doing something like 1 divided by the square root of 2 would have been a pain, but doing the square root of 2 divided by 2 was not that hard using long division. So they banned the use of radicals in denominators. Culturally, it has become acceptable. In fact, on the SATs, if your answer has a radical in the denominator, they won't even mark it right. So this is like the standard way of writing square roots and radicals is you don't leave them in denominators. Although, mathematically, they are equivalent to a simplified answer. Okay, so there's my little spiel on radicals. So let me get some good problems going here.
What?
That's true too. True statement. Wednesday, Thursday, Friday. So guys, check this out. What if I've got the square root of 5/4? And I want to simplify that. Now, do you know what number multiplied by itself is 1.25? I don't. Or 5/4? No. However, what if I distributing radicals over quotients? Hey, and look at this. Can I simplify any of those? Square root of 5 over 2. And in fact, I'm done because I got rid of my radical in the denominator. Yes. Denominator.
So which day did you start?
Wednesday, Thursday, Friday, but don't worry, internet viewers. You probably are in the future and kneecaps doesn't even exist anymore, so don't worry. So guys, let's keep going. What's another good problem here? I'm going to jump right into this. 5 over 2 square roots of 2. Well, actually, let's just do straight up square root of 2. Square root of 2. Now, we got a problem, friends. I've got a radical in a denominator. I'm not supposed to have a radical in a denominator. Mathematicians don't like that. So... Ooh, what times itself equals 2? Let's see. That's not the way I thought about it. So I'm trying to think of. Oh, okay. You're actually trying to answer what is that square root. The answer to that question is approximately 1.414, but no, that would be a decimal. I want to have a non-decimal. So I see your question though. So it doesn't simplify. Now, if I want to change the way this fraction looks, now recall back in the day. Maybe I should do a little recall here. Let's do a recall. If I wanted to do this, 2/3 plus 1/6. Oh no, I've cornered myself. Man, I can't believe I just did that. Mentally, I've just sabotaged myself. The answer to this question is the number I hate the most. I can't believe it. I'm sorry. How did I do that? How did I do that? So anyways. Okay, how would you have added those fractions? And the LCD between these two guys is 6. And then what would you multiply this guy by? 2 over 2, right? And we would have gotten 4/6 plus 1/6 equals, that's actually a weird 6 right there. And now I could just add the numerators and I get 5/6. Ugh. Gross, right? So my point is, what did I do here and why was I allowed to do it? Why could I just randomly multiply by 2 over 2 and it didn't? Well, I was finding an LCD, but why is this fair? Why did that suddenly, why didn't that like ruin my equality between this statement and this statement? What is 2 over 2 the same as? 1. And 1 is the, ready for this, multiplicative identity. Meaning, you can multiply it by anything and it doesn't change it. Okay? So it turns out, similarly, if I could multiply this by some version of 1, I'm not going to change its value, but I might change the way that it looks. How about that, friends? So could we find the best one to multiply this by? Interesting choice. Interesting choice. Because if I multiply the square root of 2 by itself, I am in a sense squaring it, am I not? And squaring a square root eliminates it. Well done, my friend. Well done. So let's multiply across 5 roots of 2 over root 2 times root 2 is, you could either write it as the square root of 4, and that's equal to 2, right? Or you could say that's just root 2 squared, and that's going to cancel, that's going to equal 2. Or you can just say, like, that's just 2, because, yeah, I said so, right? And yeah, and there you go. So that's a clever move there. Clever move. So the thing that we multiplied by in this case, because this was a square root, I multiplied this by whatever would have given me a 2 squared on the inside. So let me see if I can actually pick it up a notch. Here we go. What if I've got, watch this, the square root of, well, no. How about 3 over the cubed root of x squared? Now, this one's actually kind of sneaky. I do want to get rid of that radical, so I want to multiply this by something. What do you think I should multiply it by? Just regular old x squared? The square root of x squared? The cubed root of x squared? Well, don't write this down yet, but watch what would happen. Multiply those, I would get the cubed root of what? X. And that doesn't actually help me. So I want to multiply it by, whatever is going to give me a perfect cube, right? I want to have this equal the cubed root of x cubed. So what would I multiply this by? X to the what power? In this case, the first, all right? So 2 plus what equals 3. I'm trying to plan ahead so that way it'll actually give me something that'll simplify, right? So cube root of x squared times the cube root of x is the cube root of x cubed, right? Let's see, can I put that in words? So I'm multiplying by a value that will give me a perfect cube. All right, so that's actually a really sneaky, tricky trick. It's kind of challenging, I'd say. So let's see, up across the top, I'll have 3 times the cube root of x is 3 cube roots of x. And let's simplify this one step further. Numerator I can't simplify, so that's 3 cube roots of x over, let's see, I don't like that x. And what is the cube root of x cubed? X. Does Connell's rule apply? Does absolute value show up?
Yes.
How would you know? No, those are both odd, so they don't show up. If both of these were even, they would. So no absolute value shows up. I've killed all radicals in my denominator, and I've obtained world peace. Wonderful. Wonderful, wonderful. Okay, so craziness. Let's talk real quick about adding radicals. And we're just about done. I'm going to actually go over to the next page. Ready? Let's talk about adding radicals. Adding radicals is done the same way as combining like terms, which you might recall from the days of algebra expressions. And the trick to combining like terms back in the day, let's do a little recall again. I love recalls. Recognize this belonged to your father. That's a line from Robin Hood, Prince of Thieves, delivered by the Sheriff of Nottingham to Kevin Costner playing Robin Hood, of course. And he was holding his father's sword. It was a pretty emotional moment. Of course, I always thought that he sounded like Carl Winslow from Family Matters when he delivered that line, which is particularly confusing. Let's see. So check this out. If I have 3x to the fourth plus 2x cubed minus x to the fourth, how could I simplify that? Which two of those, or which three of those, or which none of those can I combine?
3x to the fourth minus x.
Why are those like terms? They have the same exponent and they have the same variable. Okay? So they had two things, right? For instance, if this is a y to the fourth, it would have been a no-go. Right? So 3x to the fourth minus x to the fourth, and how do I do that? I actually would have just merely subtracted their coefficients, right? 3 minus 1 is 2x to the fourth. And the exponent and the variable remained unchanged, and then plus 2x cubed was there. So the question is, what are like terms for radicals? So here we go. Like terms, combining like terms. All right. They must have the same radicand and index. Okay, so what do I mean by that? I mean nth root of a plus the nth root of a equals 2 nth roots of a. Okay, so index, or the radicand, is referring to the inside, right? And the index is referring to the little guy, right? So because these had both nth roots and the same insides, I could combine them where I just add their coefficients. So I had one of them plus one of them is two of them. Okay? It's kind of a little bit weird, unusual, perhaps. Perhaps so, perhaps. Right? So let's simplify this. I'm actually going to jump right into the last example, so it's going to unfortunately be a more challenging problem, but that's fine. We're going to be awesome at it. 2 square roots of 20 minus 2 square roots of 45 plus 3 square roots of 80. Now, question. Are any of these like terms? Why? They do have the same, what? Indexes, right? These are all square roots, so that's cool. But the insides are different. Okay, well let's actually simplify these. Square root of 20, what's a perfect square that goes into that? 4 and 5, I like it. 45, what's a perfect square that goes into it? 9, there's the one that we wanted earlier. 9 goes into that 5 times, I think. And square root of 80, ooh, a little bit trickier. Perfect square, is it 16 goes into it? So technically 4 also goes into it, but if you reduced it by 4, you would have gotten 2 square roots of 20, and then the square root of 20 would have reduced yet again. So the best thing to do is find the largest perfect square that goes into 80, not the, just any old perfect square. So let's see, let's simplify this. 2 roots of 4, that's the same as 2 times 2 roots of 5, minus 2 times 3 roots of 5, right? Because square root of 9 is 3, plus 3 times 4 roots of 5, because the square root of 16 is 4. We're getting there, we're getting there. And 2 times 2 is 4, not a trick question. Hey, look, they're buddies. 2 times 2 became 4, bam. Minus 2 times 3 is 6 roots of 5, plus 12 roots of 5. Good save, good save. And now question, do I have any like terms? All of them. What part on this last step were we thrown off?
Like just like 2 times 2 is the root of 5.
Okay, so how did I get from here to here?
Yeah.
Well, I simplified the square root of 4 to get that 2. And right, these were all being multiplied, so I wrote it as 2 times, what was the square root of 4? 2 multiplied by the square root of 5. So that's what I was just going through and simplifying the ones that I knew were perfect squares to their respective answers. And then now I just multiplied, right, 3 times 4 is 12. So, okay, so these are like terms because, ready? They've got the same indexes, indices, I don't know, and the same radicands. Those are all 5s, right? So, let's combine them. I've got 4 apple pies minus 6 apple pies plus 12 apple pies. So 4 minus 6 is negative 2, plus 12 is 10, and they don't change the fact that they're apple pies just because there's 10 of them now, right? So the index is still the same, and the radicand is as well. So I just want to point out, notice we did both addition and subtraction in this problem. So I guess I could actually call this adding / subtracting radicals, but that's fine. So, all right, internet friends, thanks for watching. Hopefully you learned a lot about radical expressions. Rock on.